All right, nerds. Now's the moment you've all been waiting for when we start talking about dividing complex numbers. But it's important that we remember while we're dividing complex numbers that we're going to use the complex conjugate. Mucho importante there. Okay? So, first, I'm going to explain to you mathematically why we have to go and use the complex conjugate, and then I'm going to give you a literal illustration of why it's important that we do that. Okay, so first off, we're going to do the proof of what a conjugate does. In the last example that we did in the notes the other day, we saw that when we multiplied a complex number by its conjugate, its product was a real number for that specific example, but now we're going to go and do a generalized proof of it. So let's say that we've got some complex number a plus bi, whose conjugate is obviously going to be a minus bi. Well, if I go and multiply these together, again, using the distributive property, I'd say a times a is a squared. I'd say a times negative bi is negative a b I. Okay, I would continue doing my distributions and say bi times a is positive a b I. I'm just writing in an alphabetical order. And then bi times negative bi would be negative b I squared. Right? So we would notice that we have two terms that eliminate each other. They sum to zero. Negative ABI and positive ABI, those will simply undo each other. This I squared, well, that's going to turn into a negative 1. So this just becomes a squared, then minus um, b squared I squared. Because I guess I probably should have gone over here and put a set of parentheses around that, because that certainly makes it a little bit more sensical there. So this I squared that's over here, well, that's going to go and turn into a what? A negative 1. And what's negative 1 times negative b squared? Well, positive b squared. So it's just a squared plus b squared, right? So this is a real number. Okay, there are no i's in it, so it's only a real number. It is a pure real number. Okay, and why is it important when we're doing division that we end up with like a real number somewhere? And that comes from the following illustration. Okay, now I realize that we're all doing digital learning and stuff like that right now, but I'm going to try and illustrate this for you. Now, some of you may consider yourselves to be artists. That's okay. You can be an artist. You're just not going to be as talented as I am. I'm about to draw for you something that is going to be so realistic and lifelike that you're going to want to like rub your eyes and look at the screen, because it's going to seem from this blank canvas that is presented in front of you that just the most beautiful thing you've ever seen in your life is coming out at you. Okay. So what we're going to do is we're going to draw something. And by we're going to draw something, I mean I'm going to draw something. You're going to be insanely jealous of how talented I am. But anyway, enough bragging about me. You ready? Here it comes. All right. Now, I know what you're thinking. How was he able to draw the world's most lifelike unicorn on a smartboard in the middle of a global pandemic? Okay, some people just have talents. Some people will never be able to compete with those talents. You may be one of those people and probably are, but that's okay, because each one of us has our own unique gifts to the world. Mine is drawing the most realistic unicorns that you've ever seen in your entire life. Yours is probably something less cool, but could still be valuable to somebody somewhere. I don't know. But why did I go and draw this incredibly lifelike picture of a unicorn? Well, simply to illustrate something. Okay, this right here is a unicorn. And this unicorn can go through and it can do things. So it can run around. It can go, wee, look at me, I'm a unicorn prancing all around the meadow. And then while it's doing that, you come over because you see this unicorn and you're like, yo, dude, we got to chat. So you're all like, hi. Okay. And I realize you're all looking at the board right now and also thinking to yourselves, oh my God, how did he manage to capture my exact likeness so quickly? I have talents. Okay. It's just what happens. All right. But you go through and you say, hey, Mr. Unicorn or Miss Unicorn or whatever, okay, how are you doing today? I'm doing great, except for I'm kind of coming apart, so now I need to like group it together. There we go. Hey, you want to play some super fun games? And the unicorn's like, yeah, we can play super fun games. And you can be like, oh, yeah, let's play leapfrog. So here's what you do. You go, wee, I'm going to jump. Woo! Over the unicorn, and then all of a sudden you realize that your natural talent is not actually jumping because you're now impaled on top of the unicorn. And that's how you met your demise. It's terrible. The unicorns are like, hey man, you okay? And you're all like, eh. And the unicorn's like, man, this is why I don't have any friends. Okay, but why would we go and do this incredibly graphic, realistic, lifelike drawing of a unicorn and you playing leapfrog with it? It's because I have a very, very, very important piece of life advice for every single one of you. Okay, and that very, very important, critical piece of life advice is that you should never, ever play leapfrog with a unicorn. Just don't do it. It's not worth it. Don't play leapfrog with a unicorn. Okay, so how does this relate to complex numbers and complex conjugates and dividing? Well, very simply, a unicorn is imaginary. And this line isn't really a line, it's a fraction bar. So you can't have an imaginary number in the denominator. Yay! See, we all learned something and you're never going to forget it because you're always going to remember the unicorns, okay? We can't divide by an imaginary number, and because we can't do that, we have to have a way to make it uh, uh, real. Well, it's a good thing that we have a method to make it real, and that's using the complex conjugate, baby. All right, so let's take a look at 4 examples of how we can actually do that. So we're going to do 2 of the simple case and 2 of the more challenging case. So the 2 that are the simple case are where we have just a pure imaginary denominator. Okay, so I'm going to look at this first example, and my denominator is 2i. That's a unicorn. It's a tiny unicorn, but a unicorn nonetheless. So if I'm going to do this division, I can't leave an imaginary number in the denominator because I can't play leapfrog with unicorns. So how can I get rid of that? Well, I need to go through and identify what the complex conjugate is. Okay, so there's 2 ways to think about it, but I'm going to encourage you guys to do the easy way. The more complicated way would be to say, oh, well, this is really 3 and 2i expressed as a complex number where it has to have a real and an imaginary component would be 0 plus 2i. Okay, so what is the conjugate of 0 plus 2i? Well, you might say 0 minus 2i. Okay, but could you do 0 minus 2i a little more simply? Sure, you could just do like negative 2i. But what we're going to do is we're going to multiply both the numerator and the denominator by that negative 2i. Okay, why do we have to do it to the numerator and the denominator? Well, because anytime that we multiply a fraction or rational, such as 0 over 2i by something, I have to multiply the numerator and the denominator by the same thing so that it will stay equal. If I do different things to the numerator and the denominator, then it's no longer equal. So I wouldn't be able to write this. Okay? So if I go through and do some basic multiplication here, 3 times negative 2i is negative 6i. And down in the denominator, 2i times negative 2i is negative 4i squared. But what does that little I squared turn into? Well, that turns into a negative 1, okay? So this is really negative 6i over 4. But could we write that in a simpler form? Does it have a greatest common factor in the numerator and the denominator? Sure. We could go through and we could factor a 2 out of the numerator and denominator, and it would just be 3i over 2. Well, if you go and look and say, well, what could I go through and factor out? We said it was a 2, right? I wonder if it's that 2. All right, so this is kind of the more complicated way to go and think about it. For the next example, I'll show you the easier way to do it that hopefully we all just remember. Okay, but it's going to be expressed in simplest form, in standard form, as just 3i over 2. All right. So if we go take a look at the second one, instead of going through and saying, okay, well, this denominator, which is negative 6i, is really 0 minus 6i, and the conjugate would be 0 plus 6i, we can really realize that we've got just a pure imaginary number in the denominator, and if I multiply I by another I, it becomes real. So let's just do this the easier way and say 3 minus 5i over negative 6i, and I'm just going to go and multiply that by I over I. Okay, save yourself a step, because if you multiplied by 6i over 6i, you'd have to factor out a 6 at the end, so why bother doing the extra work? Okay, so this time I'm going to draw a set of parentheses because it helps remind me that I'm using the distributive property and all that other fun stuff. So I'm going to go and multiply this out and say 3 times I is 3i, and that negative 5i times I is negative 5i squared. Okay, and then down in the denominator, negative 6i times I is negative 6i squared. So I've got a pair of I squareds, which of course are really going to be converted into some negative ones. So over here I have 3i, and instead of minus 5i squared, it's plus 5. And then in the denominator, instead of negative 6i squared, it's really positive 6. But I want to write it in standard form, so this 3i plus 5 really needs to be 5 plus 3i, and that's over 6. 5 and 3 in the numerator there are relatively prime, so there's nothing that I can do to simplify. So that's just going to be what I end up with. All right, so now we're going to take a look at an example of one where it gets a little bit more complicated. Okay, so we're just going to do the complex version. So we're just going to do A, and then once we get into the group chat, we'll go through and do B together to make sure that you guys really understand it. Okay, so these ones are more complex because we have a complex number in the numerator and in the denominator. But the process that we're going to use remains the same. We're trying to find a way to use the conjugate to make the denominator real. So if I'm going to go and do that, I need to start by multiplying by the conjugate of the denominator. Okay? So what's the conjugate of 4 minus 5i? 4 plus 5i. Okay? That's definitely supposed to be an I right there. There we go. All right. And then we're also going to have 4 plus 5i. All right. So now we get to do some multiplication. So I'm going to go and throw everything in a set of parentheses, mostly because that helps me. Yep. We still have announcements. It's lunchtime here. I don't know what time it is there, but it's lunchtime. All right, so back to math. So we're going to go and use the distributive property here, but we're going to need to use it in the numerator and the denominator. Okay, so 2 times 4 gives me 8. 2 times 5i gives me 10i. Then we have I times 4 gives me plus 4i. And then we have I times 5i gives me plus 5i squared. Down here in the denominator, we have 4 times 4 is 16. We have 4 times 5i, which is plus 20i. We have negative 5i times 4, which is negative 20i. Surprise, surprise. And then negative 5i times positive 5i is negative 25i squared. So as I go through and try and simplify and combine my like terms, over here in the numerator, I know that I've got some I squareds, and it looks like I got one in the denominator as well. So those are going to do something. I've got some conjugate things that are happening down in the denominator where positive 20i and negative 20i are inverses and just undo one another. And then I've got some like terms in the numerator that I can go through and add right there. So let's just kind of simplify what we've kind of spotted already. So I'm just going to say we've got an 8, 10i plus 4i is 14i. And then instead of plus 5i squared, that's really minus 5. Down here in the denominator, we've got 16. And instead of minus 25, it's really going to be plus 25. Okay, so simplifying and combining like terms even more, in the numerator, 8 and negative 5 is going to give you 3. So we've got 3 plus 14i. And then the denominator, 16 and 25 is going to give you what? 41? Okay, and one interesting thing I want you to notice about the 16 plus 25 is it's not a coincidence that we got that. If we go back and look at our original proof, we can see right here that when we multiply conjugates together, it's always going to be a squared plus b squared. So if we go back here and look at this example, well, what's 4 squared? 16. What's 5 squared? 25. And what's 16 plus 25? 41. Okay, so that might save you a little bit of time working through some of those problems as well. All right, and since I again don't have any common factors in the numerator that I could eliminate with the denominator, it is right now expressed in simplest form. So what we're going to do is next you guys are going to hop over into the live chat thing and we'll go to whiteboard.fi, and I want you guys to start trying to work on example B here so that we can make sure that everybody's got this under control.